Okay, so we're going to introduce the t-distribution, but we want to back up and discuss a little bit about the normal first. So one of the requirements for using the normal distribution is that we know that the standard deviation of the population. So we have to know that, which means in reality, in statistics, we rarely know the populations, anything about the population, whether it's the mean or the standard deviation, which is why we take samples to determine them. But we have to know the standard deviation of the population to use the normal distribution. And if we don't, we're going to have to use the t-distribution. Now, formulaically, they're very, very similar. So let's look at the normal real quickly. So the normal, when we're working with the normal, z equals x bar minus mu, the standard deviation of the population divided by the square root of n. Conversely, the t looks almost exactly the same. It's t equals x bar minus mu. But instead of standard deviation of the population, it's going to be standard deviation of the sample divided by the square root of n. So essentially working the same way. It's just for this will be for the normal, and this will be for the t. Now, they're very, very similar. The both distributions are symmetric. They're both mound shape or bell shape. However, the t-distribution has more area in the tails. In other words, the t-distribution has a larger variance and more area in the tails. All right. And that's really important to know. That's the type of test question we like to ask. So if the dashed line represented the normal, we'll notice that the normal is a little bit taller and the t has more area in the tails. There's one huge difference. With the normal distribution, we knew that all normal curves followed the empirical rule. In other words, we had 68% plus or minus 1 standard deviation from the mean. 95% were plus or had 95% of the data were between plus or minus 2 standard deviations from the mean, and 99.7 was plus or minus 3 standard deviations. And that was the empirical rule that applied to all normal curves, regardless of where the mean fell. In regards to the t-distribution, there are numerous curves. Matter of fact, there is a curve for every sample size. So every time we have a new sample size, we have a new curve. So whereas the empirical rule, regardless of the sample size, they all followed this for the normal curve. The t-distribution, we have a different distribution for every single sample size. Now, calculation-wise, that doesn't make much difference for us. It would if we were doing the calculus, but not to find the area for the problem itself. So, but we do need to keep that in mind. As we increase our sample size, we get closer and closer to the normal. All right. So, as we said before, X bar is the sample mean, mu is the population mean, S is the standard deviation of the sample as opposed to the population, and divided by the square root of n. So basically, earlier when we were talking about the normal, we talked about the standard deviation of X bar equal the standard deviation divided by the square root of n. Here, we have the standard deviation of the sample of X bar equals S divided by the square root of n. Okay, so properties of the t. Once again, we have a different t-distribution for every degree of freedom. And degree of freedom is just n minus 1, or sample size minus 1. All right, so we have a different degree of freedom for every n minus 1, or every sample size minus 1. The t-distribution itself is centered at 0 and symmetric about 0, just like the normal. The area under the curve is 1, just like the normal. As the sample size increases, it gets closer and closer to the standard normal or closer and closer to following the empirical rule. It never does, but it gets closer as we increase our sample size. The t-distribution has more area in the tails than does the normal, and t-distribution has a greater variance than does the normal. I would make sure that I knew all of that information. Okay. So when can we use the t-distribution? And again, this is something I would definitely star. When the data is approximately normal or nearly normal, and the standard deviation of the population is not known, and there is no clearness or skewness or outliers, it's okay to use when the sample size is less than 30. So if our sample size is less than 30 and it's unimodal or normal, and we don't know the standard deviation of the population, in other words, we're having to use a standard deviation sample, it's okay to use a t. We can also use a t when the standard deviation of the population is not known and the underlying data does not follow a normal curve and the sample size is greater than or equal to 30. So n equal greater than the 30, we can always use the t if we don't know the standard deviation of the population. N less than 30 if the data is nearly normal, all right? The t-distribution should not be used with small samples unless the underlying distribution is approximately, all right? So basically we can use a t-distribution when we don't know the standard deviation of the population and our sample size is 30 or larger, or if the underlying population is approximate. So that's fairly similar to when we can use the standard deviation of means. Okay. All right. So continuing on, we want to compare the way this actually looks. So when we look at this, and we're comparing the mean, a normal to a t-distribution, and one of the things that I would like to point out is 99.7% of our data was within plus or minus 3 standard deviations. Here I have this up, it's a little bit shorter, and we definitely have more area in the tails because it hasn't come down. So in this situation, what we have is we have 68% located here. And we have a standard deviation of 5 and an n of 4. So if we were to do that, I'll pause this for just a second. Okay, so in this case, we're working with standard deviations of 5 and sample size of 4. And if I take 5 and divide it by the square root of 4, I find out that the distance between each one of these is 2.5. So this would be 1 standard deviation, and it'd be 2.5 from the mean. This would be an additional 2.5 at 2 standard deviations, and this is another 2.5 at 3 standard deviations. All right, so the distance is the same between each one of these, and this is 1 standard deviation, 2 standard deviations, 3. This is -1, -2, -3, and they have the same distance from the mean, and we centered this at 0. All right, centered at 0, that's where we're at. Now, it's really 0.994, it's not 1. So 68% is approximately 1 standard deviation from the mean. So there's 68% here. Well, over here with the t-distribution, I still kept the same standard deviation, but it's now the standard deviation of the sample. Notice I changed it to an S. Sample size is 4. So once again, the distance between these are also 2.5. And this is centered at the mean at 0. This is at 1. This is at +2, +3. This is at -1, -2, and -3. So essentially my number line is the same. But notice, instead of being at approximately 1, we're at approximately 1.9. So 68% of the data for this one falls there. Now, you're probably going, where did he get that from? So there's a couple places I can go in the calculator. So if I go to second vars, and we know about the inverse norm. Let's do that real quickly. Inverse norm, parenthesis 1 minus 0.68, close parenthesis, divided by 2. And we'll go ahead and keep the mean of 0, the standard deviation of 1. And that's where we get the 0.9944 from. All right, that's where that came from. And then it's asking us to multiply that to find out exactly how far it is. All right, now, if we want to do the t distribution, we're going to go second vars, inverse t, parenthesis 1 minus 0.99, excuse me, 1 minus 0.68, because we're going to do the 68 percentile, and divide by 2, degrees of freedom. Well, what were my degrees of freedom? My sample is size 4, so my degrees of freedom are 4 minus 1, or I could have just typed in 3 if I'd like to. And I get 1.188. So 1.1889. So a little over 1. So this would be plus 1.1889, and this would be minus 1.1889. Right? And so you notice that we're a little bit farther from here to here, because here we're just under 1, here we're just over 1. So this is at 68%. When I go to do plus or minus 2 standard deviations, second vars, inverse norm, area, parenthesis, 1 minus 0.95, close parenthesis, divided by 2, means 0, standard deviation of 1, and I get 1.96. Now, really, we've been saying that's plus or minus 2, but it's really closer to 1.96. So plus or minus 2 has 95%, regardless of our mean and regardless of our sample size. Here, if I want 95% for the inverse t, second vars, inverse t, and let's redo that real quickly because I'm afraid that didn't show up. Second vars, inverse t, parenthesis 1 minus 0.95, divided by 2, degrees of freedom. Again, our sample size was 4, so 4 minus 1. And I end up getting 3.18. So 95% is plus or minus 3 standard deviations. So this is at 3.18 would give me plus or minus 3. And if I wanted to go compare the 99.7, second vars, inverse norm, parenthesis, 1 minus 0.997, close parenthesis, divided by 2, mean is 0, standard deviation 1. 2.96, so plus or minus 3 standard deviations. All right. Doing for the t distribution, the area, 1 minus 0.997, close parenthesis, and divide by 2. Degrees of freedom, 4 minus 1, or just 3. And it's thinking about it. We find that we're almost 9 standard deviations below and 9 standard deviations above. So you can see that the t distribution is substantially more spread out. All right. Now, if I wanted the actual, how far so this right here tells me, this right here will tell me the actual endpoints. And we'll look at that when we're not centered on 0, which will be the next one. So we'll look at this again down here. All right, so now instead of centered on 0, we're centered on 3. All right, and this one is also centered on 3. We centered both of them on 3. We're keeping the same the same standard deviation of the population, standard deviation of the sample size of 4, and sample size of 4. And so this means our distance here is also 2.5, 2.5, 2.5. And every one of those tick marks represents a standard deviation. And it does for this one as well. Now, one of the things I want to show you is we have this formula here, and you'll see this a lot more beginning, not today, but later this week. I want to show you one of the things that the calculator will do for you. So if I wanted to, instead of sitting there going, well, this is going to be approximately 5.5, this is going to be approximately 8, because I'm keep adding 2.5, I can actually do that on the calculator. So let's try something out. Let's go to stats test and go to it's Z interval, which happens to be number 7. Do that again. Stats test number 7, or Z interval. And we want to make sure stats is highlighted. Our standard deviation we said was 5. Our X bar, we're centered at 3. Our sample size is 4. Let's just say we wanted to do the 68%, or the plus or minus 1 standard deviation. And I end up finding that we knew we were going to add basically 2.5 to this. So 3 plus 2.5 is 5.5. So this ends up being about 5.5. This is it's not exactly, because the empirical rule is a little bit rounded, but it's about 5.5. And we know that our lower value is going to be a little bit 3 minus 2.5, which is 0.5. If I go back and I do the same thing, stats, I'm going to go back and rerun this, stats, test, and I'm going to do a number 7. But instead of, I'm going to change my confidence level from 68% to 95%. So this should be plus or minus 2 standard deviations. And we knew that we're supposed to be about 8, and we're at 7.9, so pretty close, just by rounding. And we have a lower bound of negative 1.9. And then when I go to do it one more time, stats, test, number 7, this will do the 99.7.997. I end up with negative 4.4 to 10.4. And essentially all I'm doing is adding 2.5 and going up to here. And this way I'm subtracting 2.5. But let's compare that to see how spread out it is when we do the t-test, all right? So we're going to go back and do the same thing, stat test, except we're going to scroll all the way down to number 8. We're going to do a t-interval. We're going to keep our X bar at 3. Our standard deviation is 5. N is 4. And we're going to go with the 68%. And we're at 0.027 and 5.97. So a little bit wider, but not substantially. So this is a about 0.03, and this is about 5.9. So 5.5, this is a little larger, this is a little smaller, but not substantial. But when we start getting out further, we could go to, well, let's do the same thing. So stat test. And we're going to scroll down to number 8, t-interval. And we're going to change our confidence level to 0.95. Now we're at, now keeping in mind, so this is negative 4.95 and this is at 10.95. All right. So we have grown, because this is I mean, this is a long way out there, because this one was at negative 1.9 and now we're at negative 4.9. That's a lot farther out. And this is going to be even that much further out. And here's what I mean by that. This distance is, if this is 3, this is 2.5, this would be 5.5. This would be at 8, and this was at 10.5. This is really at 0.5. And then I take it, subtract another 2.5. This makes this at -2, and this makes this a -4.5. Well, they're telling me that 95% is -4.9. Well, -4.9 is over here somewhere. And -10.9 is over here, so, or +10.9 is somewhere over here. So we're actually off our graph already to get 95%. So 68%, it wasn't too horrible, all right? It was right around here. This was 68%. But we want to go to 95%, we're much wider. So the t distribution has a whole lot more area in the tails. All right. Hope that helped a little bit in understanding that both of them are, both the t distribution and the normal are mound shaped. Both are centered at 0. But there's a different t distribution for every single sample size, and we use the t distribution when we don't know the standard deviation of the population and the underlying distribution is normal or our sample size is 30 or greater. Thank you.